get started. Good afternoon, everyone. Welcome to today's edition of the AI4OPT seminar. It's a great pleasure to introduce Professor Ethan Modiano, who is the Richard C. McLaurin Professor in the Department of Aeronautics and Astronautics, as well as at LITS at MIT. Professor Modiano has been at MIT since 1999, and in his long and illustrious career, he has received several awards, including the Infocom Achievement Award in 2020, and he received Best Paper Awards at Infocom, twice at Mobihawk, and YOPT, and Sigmatrix. He has served as Editor-in-Chief for IEEE Transactions on Networking, and he has also served as Associate Editor for Transactions of Information Theory. He served as Technical Program Chair for YOPT, Infocom, and Mobihawk, as well as DRCM. He also served as IEEE Fellows Committee member in 2014 and 2015, and he's also a fellow of IEEE and associate fellow of AIAA. So today he's going to talk to us about his research on communication networks and the intersection of communication networks with learning. So without further delay, Mr. Modiano, for this.
Thank you very much, and thank you for inviting me to speak here today. So typically, when you hear a talk about learning, you're expecting someone to talk about deep neural networks and their application, perhaps in this case, network to network control. I'm not going to do any such thing. I'm going to talk about learning, though, but in a broad sense of learning, where I'm looking at learning as solving stochastic optimization problem, namely the network control problem, in environments that are not known. In unknown environments when I need to learn the dynamics of the system. So let's see. So I'm having a hard time seeing my slides, so I'm going to have to stand here. Can I still be seen by the camera? Because I cannot see from
the edge of the.
Okay. Well, I have to stand here because I cannot see from the other side. I cannot. The lighting makes it that I cannot see my slide. Yeah. So I'm going to let's talk a little bit about the role of learning in network control and what I'm interested in learning in network control. So basic idea, a lot of people have worked on the problem of learning network state dynamics. In particular, people worked a lot on learning things like channel state, channel connectivity, and that kind of thing has gone back for a long time, where people have applied multi-arm bandit framework to sample channels and learning the channel state. More recently, we've done work in that domain where we looked at multi-arm bandits with queues. I won't talk about that today. Another dimension is that of network control in uncooperative environments. Here, I'm envisioning a situation where I have a network, perhaps a part of the network, I'll call it an underlay, perhaps, is something that I cannot control and I cannot observe, or maybe I can observe but not control it, and I need to learn its dynamics. So then I have to solve this optimization, overall network optimization, where some of the nodes' dynamics are not under my control and I need to learn them. I'm going to talk about that today. Maybe a broader, more important general area is things like performance optimization. Can I use learning to optimize things like network delay? This often might just be a pure DP type problem, and maybe I don't need reinforcement learning for this, depending on the setup. But can we use some learning techniques to solve these stochastic optimization problems with large state spaces? And I'll talk a little bit about that. And lastly, and I don't think you might not consider this to be quite learning, but the framework of control in adversarial environments, where again, this might be more of an online learning framework. You have certain nodes in the network that maybe intentionally take adversarial action, and we need to be able to react to that by learning what they do and learning an optimal policy. And that tends to be more like an online adversarial learning framework. So we've worked on all of these things in the past 5 years or so. And today I'm going to mainly focus on two things, maybe three if I can get to all three of them. I'm going to mainly, okay. I'm going to start by talking about something that is a max weight algorithm and a learning-based max-weight algorithm for routing and scheduling in communication networks. And I'm going to give a little bit of background on routing and scheduling communication network, tell you a little bit about the traditional work in there that actually has a strong learning component to it, and then extend it in some dimensions. And then I'm going to give another example where we're solving a stochastic optimization problem for network utility maximization with unknown utilities, just based on feedback. And finally, if time allows, and I don't know if it will, I'll talk about general reinforcement learning problems for queuing networks where we have to deal with unbounded state spaces and what we can do in that context. Okay, so here is our network model just as a point of reference. And I can see now that I may have an issue that this is not my, I think this is going to be an issue. Let me take a quick look because these are my slides and I sent them to your computer and it seems like they're not showing right. So we might have to change something. Yeah, it's not going to work. I'm sorry. I'm just going to look for the important slides. If it's okay in the important slides, then we will be okay. Yeah, it seems to be okay in the important slides. So we can continue. That's fine. Some of the symbols simply didn't work, but I can talk to it. Some of the early symbols. Okay, so I'm looking at a multi-hop wireless network here. You have packets arriving. Wow, I'm sorry. You have packets arriving. They're arriving at different arrival rates. These are lambdas, as you cannot see. Lambda 1, 2, lambda 1, 4. They're arriving, and each packet that arrives has a different destination to it. So you have to solve a problem of routing. How do I route these packets from their sources to their destinations? And then also have to solve a problem of link scheduling. In particular, at any point in time, I may not be able to schedule all of the links simultaneously. And how do I decide which subset of links to schedule at any point in time? We assume that we have random packet arrivals with arrival rate. This is a lambda here, lambda C. And those lambdas are not necessarily known in advance. And the question is, how do I solve the optimal routing and scheduling problem? This is an old, this is an old problem. This has existed for 30 years now. The goal is to design a routing and scheduling policy that supports all of the arrival rate within this region. This region is the stability region of the network. For any arrival rate vector within the stability region, I want to be able to support all of the arrival rates. Again, this is a missing lambda. So the stability region is the set of all admissible arrival rates, which by definition, it means that there exists some policy that could stabilize the network with these arrivals. There are multiple notions for stability in the literature. You may have seen all of them. Bounded queue occupancy is the standard notion, but they are very closely related cousins. For example, existence of a steady state distribution or rate stability, which means that the arrival rate is equal to the departure rate. We have used all of these in our works. Today, I will actually only focus on rate stability because that's the kind of results we have today. This problem was introduced exactly 30 years ago by Tassioulas and Avramidis, and they came up with a classical scheduling policy and routing policy that stabilized the network for any arrival rate vector within the stability region. Again, I'm having a hard time knowing how to use this. Okay, so the policy is known as the max weight policy or back pressure policy. And let me explain. Let me first talk about the scheduling problem. The scheduling problem is one where only a subset of the links can be activated simultaneously. This will be because of wireless interference constraints. For example, if I have something called primary interference constraints, then a node can only transmit or receive from a single neighbor at a time. There is also something called secondary interference constraint, where nodes can only transmit if nobody in their neighborhood transmits. So for example, what I'm showing on top is a case of primary interference constraints. The set of dark links can be, this set of the bold links can be scheduled simultaneously, but you cannot add any other link to it because that will violate the primary interference constraint. What you see in the bottom is a case of secondary interference constraint. For example, the two green links can be activated simultaneously because they're sufficiently far apart. Same for the two orange links because they're sufficiently far apart, but you cannot activate, for example, this guy and this guy together. And what they showed in their classic paper, Tassioulas and Eframidis, is that the optimal scheduling policy, the one that stabilizes the network, is to schedule the max weight activation set in each time slot, where the weights are the queue backlogs. So that is to say, the optimal schedule is the one that maximizes the sum of the product of the queue size times the scheduling decision. So the queue size is the number of packets in the buffer for transmission along a long link ij. So what I've labeled here in the plot is, for example, the queue size for this link is 10, queue size for this link is 4. So this particular schedule has an aggregate weight of 14. This schedule has an aggregate weight of 12. The max weight schedule will be the one with the higher aggregate weight. It will be the 14. Repeatedly do this. The queue sizes change dynamically. But if you repeatedly do this, then the system will stabilize. The intuition is clear. I'm essentially in a greedy fashion scheduling the larger queues, preventing them from going unstable, if you would. Now, for routing, they come up with a policy that works hand in hand with the max weight scheduling. It's called differential backlog routing. They route based on commodities. Each commodity corresponds to data associated with a given destination node. So commodity C are all the packets that are going to destination node C. And along each link AB, we'll route the commodity C that maximizes differential backlog along that link. So what is the differential backlog along link AB? It's the difference in the number of packets in the queue at node A and the number of packets in the queue at node B. So for example, the queue at node A is 3, the queue at node B is 2, the difference is 1. That's the differential backlog on this link, okay? With respect to this particular commodity C. The routing decision chooses which commodity to activate on that link. It chooses the commodity that maximizes the differential backlog, the one that has the biggest difference between packets in the source, packet at destination of that link. And this is a form of back pressure to find the routes. You're basically sending the packets along the path of least resistance. It's sort of like water flowing to pipes. They're going down in pressure. Now, this is a routing decision. You still have to combine it with the link activation decision of the previous slide, with a slight modification that instead of the weights being the queue sizes on the links, we use the maximum differential backlog as the weight on the links, and then do max weight scheduling combined with back pressure routing, and this stabilizes the network. So it's a great result because it doesn't need to know anything about the linked conditions if they're time varying. It doesn't need to know in advance. It doesn't need to know anything. It doesn't need to know the arrival rates. So it's actually a learning algorithm. It's not a classical learning algorithm. This is not anything that we do with deep neural networks, that's for sure. But it uses the queue sizes to learn an optimal policy, a policy that stabilizes, okay? It does require all the nodes to cooperate. So all the nodes have to use the same policy. They have to share queue information and so forth. But it is an implicit learning algorithm applied to this. And what it's really doing, it's solving a stochastic optimization problem. It's an easy problem, it's stability. And that's why we can solve it with such ease. But that's all it's doing. It's solving a stochastic optimization problem by learning using the queue size. Using the queue size as my feedback, basically. That's my reinforced signal. So what's left? Well, the interesting thing is that okay, did it work now? Yeah. So the interesting thing is that in many settings these days, I cannot control all the nodes in the network. I don't have control over all of them. Maybe I can't even observe all of them. This can arise in situations where, for example, I'm using you know, these days, a lot of these cellular providers are sharing networks. So you can have multiple domains and one is controlled by a local provider and I'm going to use them, but I cannot control what they do. So I will feed. So, you know, a subset of the nodes are managed by another operator with a known control policy. And in this case, our existing control policies, such as back pressure, may yield poor performance. I'll explain why. So think of it as an overlay-underlay framework. I have some overlay nodes, and they rely on some underlay network that I cannot observe or control, or maybe I can only observe partially. And now, how do I solve this control decision? How do I make control decisions here? Again, so the overlay architecture, like I said, think about it. I'm operating over a cloud or a black box. I don't know what's going on inside it. Like I said, over-the-top service providers in modern cellular systems will do that. Coalition networks in military applications will do that. I got to make network control decisions based on end-to-end feedback because that's all I have, and try to learn the dynamics of the underlay. What can I do here? And what we do, I'll talk about it to some extent, is a combination of reinforcement learning as well as Lyapunov optimization to develop control algorithms based on end-to-end feedback. I'm going to focus on two things, stability and utility maximization. First, stability. Okay, so the first thing I'm going to do is I'm going to talk about this algorithm we developed in recent couple of years called Tracking-MaxWeight, which is a learning-aided max weight algorithm that allows me to learn the unknown underlay dynamics. Here, the focus is purely on stability, so it's a fairly easy learning scheme. And then I'm going to extend it and talk in the second half of the talk about, in the second part of the talk about some generalizations of these ideas. So let's start. So the model, I have a queue in networks with n nodes and k flows. Qik is the size of the queue of flow k at node I at time slot t. In each slot, I observe some network event omega, which is an external event, and include things like random link capacities, packet arrivals, and so forth. And I'm assuming that these are stationary processes. Each node I needs to make routing decisions. Fijk is the offered transmission rate on link ij with respect to commodity k or flow k. And that's the offered rate. Fijk tilde is the actual transmitted packets, which may be smaller than Fijk, because if I don't have enough packets in my buffer, I may transmit fewer than Fijk packets. So that's the model. A little bit more. My network is partially controllable. So the set of all nodes is denoted by n, and the routing vector is f. But that set of all nodes, it can be divided into a subset of controllable nodes C, whose actions are f sub c, and a controllable policy pi sub c, which is a mapping from the network state and the event to the flow variables. But also have a set of uncontrollable nodes, which I denote by u, which take actions f sub u, which I cannot control. And sometimes I cannot observe, or maybe I can only partially observe their actions. And they have an uncontrollable policy. I'll say a little bit more about the uncontrollable policy. Our objective is to design a policy pi c for the controllable nodes. That's all I can do. That stabilizes the network. And here I'm going to focus only on rate stability. That is to say that the queue size grows sublinear in T. It's equivalent to saying that the arrival rates equal to the service rate. All right. So I'm going to first focus on queue agnostic uncontrollable policy. That is to say the policy at the underlay nodes, the uncontrollable policy, is a mapping from the random events to the flow variables. And the network event, so the network state, the queue sizes is not being used by the uncontrollable policy right now. This is a limitation. However, it allows for the problem to be tractable. It is and it covers a large number of practical protocols. For example, shortest path routing is a stateless algorithm. Multipath routing is stateless. Randomized routing is stateless. Any of those do not take the queue size into account. So that's the first part. So even in this context, back pressure that I just showed you, that routes packets from nodes with a lot of traffic to nodes with less traffic and is known to be stable, in this setting, it fails. Look at a simple example here. And in this simple example, these are the link capacities, what I'm showing, but these are underlay nodes, 2 and 3. 2 and 3 take uncontrollable actions. I cannot affect their control decisions. And those are, like I said, stateless actions. Node 2 always transmits all incoming packets to node 3. Node 3 transmits nothing to node 4, just holds everything. Okay, it's a trivial example, but I'm just going to show you what happens. Okay, now, if you look at these link capacities and you wanted somehow to find the best route for this flow from 1 to 4, a flow of 20, you might choose this route if you didn't know better. But if you know better intuitively, you know that node 3 is going to hold on to all your packets and you'd send them down this route. What back pressure would do, back pressure would look at the queue size at node 1, as it has arrivals, look at the queue size at node 2. It notes that queue size at node 2 is always 0, and it will send packets to node 2. The queue size at node 2 is always 0 because node 2 always sends its packet to node 3 immediately. So node 1 will send all of its packet to 2, and they're all going to be held up at node 3, and the system will be unstable. Trivial example, okay? But nonetheless, it just shows the point that I cannot do back pressure if I don't know what the underlay is doing. You can come up with more sophisticated examples if you want to, but I didn't want to. So why does back pressure fail? Well, I mean, node 3 is not being fully work conserving. Back pressure is not aware of the behavior of node 3. And the lesson learned from it is that a good control algorithm has to know what the underlay nodes are doing. It has to know better. It has to know something about what the underlay nodes are doing. I guess that's kind of intuitively obvious. So we developed Tracking-MaxWeight, and the idea behind Tracking-MaxWeight is we're going to try to learn what these underlay nodes are doing. That's it. So the way we're going to do it is we're going to enhance the original MaxWeight algorithm with an implicit learning of the policy used by the uncontrollable nodes. And what Tracking-MaxWeight does is it produces control actions for uncontrollable nodes. These are implicit control actions. Control actions for the controllable nodes, and also generates implicit control actions for the uncontrollable nodes. We call them emulated actions. These are actions that we wish the uncontrollable nodes would take, at least initially, but it's not what the uncontrollable nodes are going to take. And we're going to try so what's going to happen is Tracking-MaxWeight will aim to stabilize a virtual system with emulated uncontrollable actions. By that, I mean, it's not that we wish that this is what the uncontrollable nodes would do. It's sort of what we wish they would do, but we also take into account what they actually are doing. And I'll show you what I mean. So it will try to stabilize a virtual system with emulated uncontrollable actions, and also minimize the gap between the emulated system and the true uncontrollable actions. So that's the trick. And so the details. So I'm going to let F sub U be the true action taken by uncontrollable nodes. Now, G are the flow variables that Tracking-MaxWeight will generate. It will include both controllable actions for the controllable nodes and uncontrollable actions for the uncontrollable nodes. Okay. There will be a gap between the actual actions taken by uncontrollable nodes and the emulated actions by G. Okay. This gap I'll denote it by delta. And it's exactly the difference between what really happened and what I hoped would happen using my emulated actions, the Gs. Okay, so next. I have two virtual queues. The first virtual queue, call it X, maintains the backlog in the emulated system. What I have here is the queue length update in the virtual queue of emulated system which includes arrivals minus departures, all using the emulated control actions. This is not really happening. This is what I think is happening. Or what I think is happening if the underlay really took my actions, the actions that I wanted to take. Then I will have another virtual queue that characterizes the cumulative difference between the emulated actions and the true actions. Here, y at t plus 1 is y at t plus the delta term, or the delta is the actual difference, is the difference between the emulated actions that I wanted for the underlay nodes minus the actual actions taken by the underlay nodes. And notice that this, as I describe it, requires the ability to observe the actions of the underlay. But it will also work if I have sparse or noisy observations, as I'll show in a moment. So that's the system. Now, the Tracking-MaxWeight algorithm, in each time slot t, it obtains G by solving the max weight solution. Notice this is the classical max weight scheduling here. And the weights here are exactly the differential backlog weights, except now they're a little bit different. These are not the queue sizes. These are the virtual queue sizes that I described for the emulated actions, minus the gap between the real system and the virtual system. So we take these actions. So what happens? I solve for these flows. I solve for the G. I apply the controllable part of G to the controllable nodes. For the uncontrollable part of G, I just update my virtual queues. So what does Tracking-MaxWeight do? It uses back pressure on the virtual queues, offset by Y, which is the difference. So if the difference between my emulated action and the actual action taken by the underlay gets large, then you can see that Tracking-MaxWeight will drive me away from using this link. That's the idea. And yeah, now, so the offset Y drives the emulated actions toward the actual actions and drives the gap to 0, which is what we have to do. We cannot have a gap. All right. So if you look at this example that I showed you fails, you can just see exactly what will happen here. And what will happen is this Y34, the difference between any emulated action I come up with and the actual actions will grow. It will continue to grow as long as I'm sending packets along this path, because I will think that node 3 is forwarding packets to 4. The reality is that it's not. Y34 will get big. As Y34 gets big, it causes a back pressure to the source, and I will not send any packets that way eventually. And then the network will eventually stabilize on the right policy. And I will send the packets all going down 154 eventually. And that will stabilize, good enough. So this is our first result. If the uncontrollable nodes use an omega-only policy that makes decisions based only on, does not take into account the current state, just the random events, the network events. And if the state can be observed, then Tracking-MaxWeight will stabilize the queues whenever possible. We show this, not super complicated, long, but not complicated. We show that Tracking-MaxWeight can stabilize the virtual queues X and Y. Y is the gap between the virtual queues and the real queues. If that gap is stable and bounded, then it tells you that the actual queues are also stable and bounded. That's the basic idea here. What happens if I have sparse observations or delayed observations? If my observation, say tau I, is the most recent time I observed node I, and if I let Li of t be the gap in the delay in observation at node t, then if the observation delay summed over all time is small o of capital T, this is going to be a regret type bound here. If it's small o of capital T, so it goes sublinearly in T, sorry, the algorithm will stabilize the queue whenever possible. Again, so as long as we have observations delays that are sublinear in T, so constant delay that goes the square root of T, but T is my time horizon, any of that will work. Okay, what about noise? If I have noisy observations, which might arise in settings where I cannot truly observe the queues, but I can estimate them based on some end-to-end measurements, but my estimates are reasonably good, then again, we'll have stability. How good do they have to be? Not that good. As long as the estimation error is small o of T, which includes the case of constant estimation error, then Tracking-MaxWeight will stabilize the physical queues whenever possible. So as long as estimation error goes sublinearly in T, Tracking-MaxWeight is throughput optimal. So yes.
So do you only do routing or do you also do scheduling?
This setup, as I describe it, only discusses routing. It will apply to scheduling just the same, I believe. Yeah, I'm pretty sure it does. Yeah.
So whenever possible. So I understand that because you have this uncooperative noise, the stability region will be smaller.
Right.
So can you characterize the smaller stability region for given behavior of the?
Yeah, I think so. Yeah. Yeah. The question is, can I? What does whenever possible means? It means that given uncontrollable nodes behavior, I should be able to characterize the stability region, and we do, of the network subject to the uncontrollable nodes behavior. In the case that the behavior is stationary randomized, as I was describing here, that's straightforward. If the behavior is queue dependent, it may be less straightforward. Okay, it may still be doable. I don't know, but maybe less straightforward. Okay, so we got all that. Quick simulation results. I don't love simulation results, but somehow you have to have them. So I'll show them really quickly. Here I have 3 uncontrollable nodes that take sort of random routing decisions between them. I have arrivals at 1, 2, 3 nodes and departures potentially at 3 other nodes. All the link capacities are 5. Let's just show you what I want to show here. We designed that particular example so that to show that in this case, max weight will be not stable. This is the queue size and this is time. You can see that traditional max weight will go unstable, but tracking max weight with various values of L is the delay in making observations, is stabilizing enough. If you zoom in on these 3 plots here, you can see that larger values of L give slightly larger delay, smaller values of L, fresher observations result in smaller delay. Stability is preserved in either case. If I look at this, this is a nice one. What's really interesting here is these, you know, I had three unobservable nodes. So I can look at the gap between the emulated queue size, which is what I think it should be, and the actual queue size of those nodes. And you can see that the gap is stable. So it means that I kind of able to learn the actual flows on those queues. So I was able to learn that. Finally, tracking max weight with noise, different levels of noise, all sublinear in T, all seem to show stability. Interestingly, we even have tried with node that is not sublinear in T. And in this particular case, we're able to show, it seems to show that it's kind of working anyways, even though the noise happens to be linear in T. Because actually all we had is a necessary, a sufficient condition, but not a necessary condition. But I'm pretty sure I can show you that if the noise is linear in T, there exist systems that I cannot stabilize. It's actually pretty obvious to show that. Because I can always have, if the noise is linear in T, I can always make the noise mask the queue size. All right, so let's move on. Any questions before I move on? Yes.
Controllable policy being admissible would depend on that, right? Admissible.
Which one? The controllable or the, I'm sorry.
Even the uncontrollable policy, your controllable admissibleness of the controllable policy will depend on that, right? Because you have interference and
No.
Okay, gotcha. Got it. I see what you're saying for this. Okay. as I did, thank you. That's actually a great question. Yeah, he was asking me the same question, but implicitly. Yeah, if I had a scheduling component in addition to the routing, right now I really talked about routing. If I had a scheduling component, this would require careful thought. I think you're correct. If I had an uncontrollable scheduling, and the truth of the matter is that we've looked at that as well. And I was telling Siv that it is also generalizable for that setting, but it's not trivial. It's not immediate, because I think I've long been interested in a case where I'm trying to schedule in a network where some of the nodes are controllable and some are not, and that's a problem that is, I think, very interesting in of itself as well. So yeah, good question, good point. I think that in that context, if you knew what the uncontrollable nodes are doing for scheduling and you solve the max weight scheduling under that constraint, you'll have stability as well. I think that's correct. Okay, so now let me move on to something that's a bit closer to what you would consider learning, and it's a gradient sampling approach. So now I'm still looking at a similar network setting, but now I'm trying to do network utility maximization. So let me tell you what network utility maximization means. Network utility maximization refers to the problem whereby there is utility associated with allocating a rate to a given traffic stream. So I don't have just arrivals, but I get to decide on the arrival rates for different flows. And I get the utility R, G of R is the utility of allocating rate R to class I traffic. So GI of R is the utility of allocating rate R to, so, you know, utility can be logarithmic in R to represent something called proportional fairness. So it could be linear in R to represent maximum throughput, or whatever you wish to make. And this network, so the objective of NUM, network utility maximization, is to maximize aggregate utility subject to the rates being within the network stability region and certainly being less than the arrival rates. That's the classical utility maximization problem that's been addressed by us and others for nearly 20 years. The novelty arises that in many settings, utility functions are not known. So a lot of us have addressed this problem by saying, oh, we can solve it given any convex utility function. Great. So you can decide that your utility function is logarithmic, and now we can solve this and come up with a dynamic control policy. We've done this. But what happens when you don't know the utility functions? Why might that even arise? Well, it might arise, for example, if the utility function is the quality of the video that you're transmitting, and different video qualities and different rates, and you don't really know how it's going to play out at the end user, and you can just make decisions based on feedback, just as an example. Or maybe you have some kind of a computation task, and the utility of the computation task is a function of your data rate, but you don't really know what it's going to be. Or it might be trying to optimize network delays, which I cannot characterize. I'll talk about that in a bit. So that raises very interesting new challenges, and I need to learn the utility function. Could be the power consumption of links, user satisfaction in general, and I have to do it based on feedback delay. So here we combine ideas from scheduling and utility learning and NUM, utility maximization. And the key idea behind this work is gradient sampling. So we call it gradient sampling max weight, but the idea is we use feedback to construct approximate gradient of the rates R. So we're going to choose user rates RIs, and we're going to use feedback on the utility to compute the gradient. Okay, that's the idea. So you can imagine a setting, as I show here. I will use rates Ri plus delta, Ri minus delta, measure the utilities, compute the gradient. Then after I do that, I will combine that with max weight scheduling and back pressure routing to make the routing and scheduling decision. That will help me ensure that the network remains stable. And then I will update the rate variables using an appropriate gradient that includes the queue length. So I update the rate variables by taking the gradient into account, which I computed up here, looking at the queue length at the source nodes and subtracting that. So the queue length will basically drive the rate smaller. You can almost look at this if you know, in the paper, we make the argument that this has a primal dual type interpretation where the primal variables are the rates, which I update with the gradient. The dual variables are the queue length, which correspond to the constraint that I need R to be within the network stability region. We update the primal and dual variables based on the gradient of Lagrangian and the queue length dynamics and so on. So that's the intuition behind it. The proof is based on the combination of Lyapunov techniques as well as gradient analysis. A very interesting part, I'm not going to spend much time on this gradient sampling algorithm right here, but a really, really interesting thing that arises in this, and it's completely counterintuitive, in my opinion, is that I can make a decision on a rate R, and I make that decision, and it's going to be subject to queuing delay before I observe the utility. So I'm not going to get my feedback for the gradient for some time. Meanwhile, what am I doing? What am I going to do while I'm waiting for the feedback? How do I update? Can I keep the old decisions? Well, it turns out that you make this decision, and if so anyway, it turns out that if you make the decision and keep the decision static until you get the observation to update, that will not work. It will result in it will not result in sublinear regret. That will not work. So we devised what we call a parallel instant algorithm, where we suppose the feedback delay is known to be Z slots. Then I will run Z parallel versions of gradient sampling. Each one of those versions gets immediate feedback, of course, with the Z delay, but each one of them is updated freshly. Okay, so I'm going to do that. So that solves the problem, except that solves the problem that will give me sublinear delay, regret. The problem is that Z is not constant. Z is the queuing delay. So we actually came up with a scheme where we run parallel instances dynamically. We generate new instances dynamically while waiting for feedback, and we keep a queue of those instances. And it's a very elegant solution, extremely cute, maybe the best part of that paper, in my opinion, on how to apply gradient sampling to a queuing system. The bottom line is that we're able to show that we measure regret, the cumulative difference between the utility achieved over a finite time horizon versus the optimal that can ever be achieved. We show that when the feedback is noiseless, we achieve regret that is square root of the time horizon. When the feedback is noisy, in the interest of time, I'm not going to go into the detail, the regret is potentially a little bit greater, not much. It can be as high as T to the 2/3, depending on the noise parameters. Regardless, we're getting sublinear regret, which means we're getting optimality in terms of the utility as time goes large. So real quickly, you know, I'm going to skip all of this. I want to talk about something more interesting. I'm going to skip the example. So this idea of gradient sampling gave rise to another idea that we just published, which is to use gradient sampling for minimum delay routing, to solve a minimum delay routing problem. So let me describe the minimum delay routing problem. Suppose I have k paths from the source to the destination, and I need incoming traffic of rate lambda, and I need to route it along one of the k paths. And now I can split it. I can split it along the k paths. So I want to compute the optimal rates R1 to Rk. Okay. I'm going to let the flow on link E associated with some rate vector R to be the sum of the sum of the Rk on all that for all the paths that traverse link E. Okay. And then the delay associated with the link E is a function of the flow on link E. So the delay is a function of the flow. We are going to assume that this delay function is convex in the flow, non-decreasing, and we're going to assume it's convex and non-decreasing. There's been work on this in the past. Gallagher formulated this problem in 1997, so that's a couple of years ago, 45 years ago. And he assumed that the delay function was known. And he formulated this convex optimization problem. It's in his textbook. If you have his textbook's data networks, I think I saw you have it. Then you can find it in chapter 4, maybe 5 at the end. So this optimization problem. The issue is that these delay functions are not known. You just don't know. So what's going to happen? So let's take a look at an example. Suppose I had 3 parallel MM1 queues. If I have 3 parallel MM1 queues, I have a Poisson arrival rate lambda. If they're all identical, it's pretty obvious that I should send the rate of lambda over 3 to each of them. And that will minimize delay because of the convexity of the delay function here. Oh yeah, the delay function for MM1 queues is clearly convex. That's what it is. Okay. But what if I had a more complicated setting? Suppose in this example, I have 2 MM1 queues, exponential service times, and 1 queue which is deterministic service. Now, intuitively, splitting it 1/3 doesn't make sense anymore because the deterministic service queue will clearly have lesser delay than the exponential queue. So I should send more of the traffic to this one. How much more? How do I figure that out? Well, maybe you can solve it if you have the formulas, which we do, and you can solve in this case. But what in more general cases? Can I solve it? Well, the delay function will depend on link characteristics. If they're wireless links, the channel characteristics, I don't know them. I need to learn them. What do I do? So here we said, let's apply gradient sampling. So exactly the same idea, but now I want to find the rate vector R. This is not the arrival rates as I did before for the utility maximization, but this is the splitting rate along the different paths that minimize D of R. And I can do the exact same trick. I just need to now learn the delay function and the optimal static routing solution. Now, we make an assumption also that the delay function is convex. Maybe 15, 20 years ago, my student Mike Neely and I showed that it is indeed convex for single queues, general single, any service queues. In this work, we actually are able to extend that result to tandem of queues as well as networks with disjoint paths. Generally speaking, assuming convexity on delay functions is not a bad assumption, but it's not trivially obvious that any system is convex. But it's a reasonable assumption. That's our assumption. Another comment I want to make here is that we're looking at static routing. I'm looking at lambda, and I'm going to split it along the paths in a static fashion. But you can also envision policies that make decisions based on the queue size, such as max weight, and those could perform better. Okay, we are restricting our analysis to static policies that just split the rate vector along the k paths. You could potentially perform better if you're allowed to make decisions based on queue sizes, but we will show through simulation that our static policies outperform common dynamic policies. And I'll also point out that solving for optimal dynamic policy is absolutely impossible after many years of experience and trying. So again, we apply the gradient sampling methodology. It's nearly identical to what I described before. I will just add a couple of caveats. There are some interesting caveats here. We need to approximate the gradient with respect to the rate vector R. To do so, we make a random perturbation of the rate vector, epsilon random perturbation. We measure the rate, we measure the delay at R plus delta epsilon, R minus delta epsilon, and use that to compute our gradient, estimate of the gradient, I should say. This gives rise to challenges. How do we get the delay at these particular rates, RT plus, how do I get the delay at RT? How do I solve the value of D of R? I'm going to have to do it based on observation. But I'm trying to solve a static routing problem. What does it mean to observe? It's not going to be the immediate delay of this packet. I need to make sure that the system achieves steady state before I can make that observation. So there is some analysis that goes into this. So for example, if I use the queue length to estimate the end-to-end delay, then, if I use a static rate vector R for some time duration tau, as tau goes to infinity, in fact, I will achieve the steady state delay. So I can use the queue length at time tau t plus tau as long as I make tau long enough, and I'll talk more about that. The key thing to notice is that the difference in the queue length at time t plus tau and the steady state decreases exponentially fast with tau. That's, I guess, sort of well known that I approach exponentially fast. You can analyze the convergence of a countable state-state Markov chain using Lyapunov drift argument. So it decays exponentially fast. So I need to observe for some amount of time tau. Naturally, you can see that tau probably has to be logarithmic in my time horizon. So that's exactly what we end up doing. Our gradient sampling policy, and I realize I'm hurrying a bit now, measures the, chooses a static rate vector, perturbs it by epsilon, uses it for a duration of time log capital T, then perturbs it by epsilon in the other direction, and use it for duration of time also log T. So I do R plus epsilon, R minus epsilon. Then I use that to approximate my gradient. And the ultimate result is that we're able to obtain a delay optimal policy. The difference from the delay optimal policy and our policy is, again, very sublinear. The solution, it requires proper choice of the parameters, and it involves analyzing the bias and the variance of the approximate gradients, because these are approximate gradients and not the exact gradient. We need to bound those, the bias and the variance, plug it into dynamics of the gradient descent algorithm to show this result, but it all holds and it leads to an optimal policy. Real quickly, maybe this is an example where you see this link, type 1 link, I'll call it, it has deterministic service time. Type 2 link has uniform service time, and type 3 is very, very bursty. So naturally, you'd want to send most of the traffic along this link and less along this link. We run this algorithm, and indeed we show under different load levels that here is the solution in terms of gradient sampling. The result of gradient sampling gives me the lowest delay, sometimes by far. The highest delay in orange is just uniform routing, splitting the traffic in 3 along those 3 paths. And interestingly, the one here in orange is join the shortest queue, which is a very known policy for minimizing delay that is queue-based. And we beat join the shortest queue, which is very interesting. Consistently beating join the shortest queue. You can look at it also in terms of 3 paths. Again, here I have one path that's deterministic service time, bursty, and uniform random. And again, very similar results. We beat, with gradient sampling, we beat either the uniform policy by quite a lot, or even the join the shortest queue policy, which is known to be very good. Join the shortest queue is version of back pressure, in fact. We experimented in many settings. This is a more complicated network example. The Abilene network, really old network that's available out there. Again, gradient sampling outperforms everything else we could think of, outperforms back pressure by a ton, and back pressure is reasonably good actually, and so forth. We extend it to wireless network where it involves both link scheduling and routing, and I will not give all of these results because that's too much. The last part of my talk was talking about actual reinforcement learning in QA networks, but I will skip it and just maybe summarize that network control algorithms, there's been a rich amount of work for maybe 30 years. They usually assume known dynamics, controllable dynamics, and the uncontrollable dynamics, unknown dynamics give rise to learning. That's really my message. Learning for achieving stability is relatively easy. It's accomplished by just monitoring the Q dynamics, and the Q dynamics provide us, maybe call it a sufficient statistics informally, and to learn the optimal policy. It is a stochastic optimization problem. People that look at the back pressure policy have long argued that it has a nice primal dual interpretation to it. Learning for optimizing network performance is a lot more challenging. So optimizing things like delay is more challenging. Gradient sampling max weight approach, I showed it for network utility maximization, for delay minimization. It has some practical limitations. I mean, if I'm going to have to wait for this system to converge for so long, I'm not sure how realistic it is, but it's at least giving us some starting point. Maybe the elephant in the room is, can we do anything with deep neural networks? I didn't say a single word about deep neural networks. I am skeptical that we can use it in this setting. I am trying to see whether one can develop a new deep neural network methodology for solving these routing and scheduling decisions without necessarily, like all of the things I talked about had some, well, not all of them, but some sense of model-based analysis. But can we just use magic and solve the problem? I think the answer is going to be not, probably not, but I'm going to try. Maybe I think the biggest challenge, and I was telling Siv that, is that, you know, you can train, you know, you're going to need to train your deep neural network on what you think the model is. But if in reality, the network and the environment is different than what you trained it for, it's not clear to me at all how deep neural nets are going to work in this setting. And there may be some mechanisms to make it work, and I don't know that yet. Thank you. Rates?
Service rate, even the distribution of it.
Yeah. So the question is, what do we know about? So I was trying to minimize delay in that very first example, and I said route to the shortest queue. Well, that's not the most sophisticated thing. You could have made it more sophisticated by taking into account rates. The answer is, in general, other than very symmetric systems, we can show nothing. So for all of these problems, we can prove nothing unless things are highly symmetric. Everything is the same, in which case JSQ will be optimal.
I have a follow-up question to this question. So what's the optimal policy? Suppose I know everything. I know the variance distribution of all the service rates. Is it known what the optimal policy is?
For delay minimization? No, that was the same question. No, we cannot solve it unless it's very symmetric systems. I mean, it goes back to like the classical server allocation problems, and I want to choose which server to serve. If it's a super symmetric system, we know how to solve it. As soon as there is an imbalance in the arrival rates or an imbalance in the service rates, everything is gone. We cannot do anything. Next to nothing. I mean, it's a DP.
Exactly.
Yeah.
If the version 2 is not working for state dependent policy, there any kind of ideas?
Yeah, fantastic. So I will just, for fun, flip to, oh, what happened to me? Oh no, So the answer is that I will just for fun flip to one of my last slides. The answer is this. If you have state-dependent uncontrollable policy, then I'm really back to reinforcement learning. Okay, I'm really back to reinforcement learning. And now the challenge is I'm going to try to solve a reinforcement learning problem over a queuing system. What is the challenge with queuing system? Is it unbounded state space? So what do we know about reinforcement learning in unbounded state space? Okay, so the thing I'm going to, that was the third part of my talk. I will not give it, don't you worry, I'm letting you go. There is some food left, I got it. I will just tell you that the problem is I've got unbounded state space. How can I solve it? Well, it's not a really impossible problem because in queuing systems, the state space is unbounded. But if you think about most queuing systems that are stable, we know that there's significant contraction. We know that the probability of the queue size getting arbitrarily large diminishes exponentially fast as long as I'm deploying some stabilizing policy. We can take advantage of that to devise what we call RLQ and reinforcement learning for queuing network policy that actually will work with unbounded state spaces, taking advantage of the queuing dynamics that I know that they contract like this. It's a theoretical result. It's not of practical significance yet that I know of. Thank you.
Let's thank Ethan again.